Hi everybody, we're going to take a look at logarithms again today, but we're going to focus on some laws for logarithms. Now, up until this point, what we've done is we've graphed exponential functions. We have graphed their inverse. So the inverse of an exponential function is a logarithmic function. We've also taken a look at some properties for logarithms. We've used our calculators and we've actually simplified some logarithmic expressions without our calculators. So we've done sort of a sampling of different processes with these logarithms, but today we're going to introduce you to two different laws. Now, the first law is something we call the product law for logarithms. Now, the product law is very simple. Basically, it says if you are multiplying two things inside an argument together, so in this case, we're using the example log base A of m times n. So that's a product inside that argument. If that's the case, if you have log base a of m times n and you want to simplify your expression a little bit, or you want to rework this expression, you'll get the same answer if you rewrite it as log base a of m plus log base a of n. So essentially what we're saying is if you're multiplying two things in that argument, so m times n, you can write this in expanded form or as two separate, simpler logs by adding log base a of m to log base a of n. Now, in order to show you that this is true, we're going to compare two results for logarithmic expressions. So as an example here, and I'm going to kind of work this backwards from the way we've presented the example. If I had the log base a, or in this case, base 10 of 25 times 125, what I'm going to show you on my calculator screen is that I get the exact same answer if I separate those two pieces of our product into simpler logarithms and say that's really the log of 25 plus the log of 125. What I'd like for you to do right now is grab your calculators and type in what you're seeing here on our screen. So in one line, I want you to type in the log of, in brackets, 25 times 125. You're going to get a decimal answer, and I want you to leave that on your screen. In the second line, I want you to type in log 25 plus log 125. Now, what I want you to recall is that if there's no base, remember that means it's a base 10, so we get to just use the regular log button on your calculator screen. What you see now is basically a screenshot of my calculator screen. So I'm proving that the log of 25 times 125, so if we have a product inside that argument, we got an answer of about 3.49. If we type it in as two separate logs and say that that's log 25 plus log 125, we get exactly the same decimal number. So we're just proving to you that the product law preserves equivalence. The second law we want to take a look at on this slide is the quotient law. And I just want to remind you about the definition of a quotient. So quotient by definition means the answer when you divide two things. What you'll notice here is this time, instead of multiplying two things inside an argument, we're showing you what happens when you divide. So if I have log base a, and again, it could be any base, of m divided by n. So this is a quotient now. We're dividing two things. If I wanted to rewrite this as two simpler logs or to separate those pieces in the argument, I could say that this is the same as log base a of m minus log base a of n. I kind of feel like these are really tied to your product and quotient rules for exponents. We know that when we divide bases and exponents that are the same, we subtract our powers. So here we're just subtracting the logarithms altogether. So we can compare the same kind of rule by applying some numeric examples. So if we were to type into your calculator now, let's say log base 10, just to make it easier to type into your calculator, log base 10 of 16 divided by 8 as an example, we would get the same answer if we typed log of 16 minus log base 10 of 8. So again, I'm going to show you what my calculator screen looks like and make sure that we verify these two answers are in fact the same. Once again, what we're proving is if you have log 16 minus log 8, we're subtracting essentially two logs with the same base. We can combine those simple logs into one statement and say that's the same as log base 10 still of 16 over 8. Now I promise if we divide that out and we say 16 divided by 8 is actually 2, log of 2 would give us the same decimal number. So again, the point of this first slide is to show you that we have two new rules. One of them is the product law for logarithms, and the second is the quotient law. So if you are multiplying things in your argument, you can separate those two pieces of the argument using addition. If you are dividing two things inside an argument, you can separate those using subtraction. What we want to do now is use a combination of these laws to complete the following examples. So it says evaluate each of the following expressions using the product law or the quotient law. And here we're saying don't use a calculator. So there are ways for us to simplify these logarithmic expressions, but we don't have to use a calculator. We're going to use a combination of some of the shortcuts that we've been learning in class the last little while and the new introduction of these two laws. So if we take a look at 3a, we're given the expression log base 5 of 50, and that's got minus or subtract afterwards, log base 5 of 2. Now, in order to use the quotient law or the product law, we have to make sure that the bases for all of those logarithmic terms match. And in this case, we can see that both of these terms are base 5. So it's okay for us to use this law. I'm going to combine these two using our quotient law sort of backwards and say if I wanted to combine these as one term, it really becomes log base 5 of 50 divided by 2. So again, quotient law means if you're dividing two things in the argument, then we're separating them using subtraction. We're just using that law in reverse. So if I simplify the argument now, that gives us log base 5 of 50 divided by 2, which we know to be 25. Now, in class, what we've been showing you is that if the base of the log matches the base behind it in the argument, we can take a bit of a shortcut. So we know 25 is a base 5 number. So I can really think about this or rewrite this as log base 5 of 5 to the power of 2. So instead of working through the whole conversion, which we were practicing over the last couple of classes, I'm just going to take the shortcut here and say, if that's the case, I know the base 5 in my logarithm matches the base behind it. So essentially those two we can ignore. Our final answer is going to be that power of 2. So log base 5 of 5 squared is just 2 as an overall answer. Again, we used our quotient rule to put things together, and then we could use some of the shortcuts for simplifying logarithms to get a single number answer or evaluate this expression. If we take a look at part B, we've got a whole bunch of things going on here. Instead of just two terms, we're dealing with three separate terms. So if we have the expression log 25, and I don't see a base, so I know my base is 10, and I'm adding log base 10 of 8, and I'm subtracting log base 10 of 2, what I can do is kind of work this one little step at a time and say, I'm adding my first two logarithms. If we look down the line, everything is base 10, so it's okay for me to put these logs together using product or quotient rule. So if we want to put those first two terms together, this becomes log still base 10 of 25 times, I'm just going to use a little polka dot here, 25 times 8. Eventually, we'll still subtract log 2 from here as well. Still a base 10, we're just creating a product out of those two terms. The reason why I know to multiply is because we had a big old addition sign when we were combining terms using product rule. So if we work this out, this becomes log base 10 of 25 times 8. We can calculate as just 200 minus log 2. So now we've whittled this down to two separate terms, and because we're subtracting those two terms and the bases are the same, we can use the quotient law. So this can be rewritten now as log still base 10 of 200 divided by 2. Now if we simplify, we've got log base 10 of 100. Now, this is when sometimes it's handy, even though we know it's a base 10 and we don't have to write base 10, sometimes it's nice as a little bit of a reminder to say, yep, this is a base 10 logarithm, and we know that 100 is a base 10 number. So again, if we convert that, we can rewrite this as log, still base 10, and then take 100 and rewrite that as 10 squared. As soon as I recognize the base of the log matches the base of the argument, I can sort of dismiss those things in my mind, and it simplifies as that power, or in this case, just 2. In our last example, it looks like we're throwing in some variables, but we also have, in this case, log base 2 of x. We're adding log base 2 of 2x, and we're subtracting log base 2 of x squared. The most important thing for us to recognize is that all of these bases match. So it's okay for us to combine the first two terms using product rule, and eventually the last two using quotient rule. So again, we rewrite this as log base 2. Don't forget your base, because if there is no base, I'm going to assume it's a 10. So this is log base 2. See, there we go. Log base 2 of x times 2x. And eventually we'll subtract log base 2 of x squared, or absorb that term in just a moment. So this becomes log base 2, and if we clean up inside those brackets, x times 2x is really 2x squared. We're still subtracting log base 2 of x squared, and because we're subtracting those two terms and they have the same base, we can change this using quotient rules. So this becomes log base 2 of 2x squared in the numerator divided by x squared in the denominator. And of course we can simplify those because the x squareds divide each other out. This becomes log base 2 of just 2. And I want you to imagine again that really there's a sneaky little power here. That sneaky little power is a power of 1. So because the base of the log matches the base behind it, our answer is going to be just 1. So log base 2 of 2 to the power of 1 gives us just 1 as a result. So again, we were able to use the product and quotient rules to simplify all of these expressions without using a calculator. There's a third law we're going to throw in the mix, and that's, again, another way to rewrite logarithmic expressions, because sometimes it's easier to leave things in, let's say, a power position, and other times we'd rather move them to make maybe your log expression a little more accessible. So what we want to show you next, and sort of the last little law we have, is something we call the power law for logarithms. So the power law for logarithms is also quite straightforward. It says if you have log base a of m, and that m is raised to the power of n. So we have the base of the log being a, we have the base of the exponent being m, and we have a power of n attached to that base. We can actually rewrite it by taking that exponent and bringing it in front of the logarithm. So that's an equivalent value to n times log base a of m. So the only thing we're doing is we're taking that power from a power position and we're moving it in front as a coefficient. Once again, we're going to prove to you that that gives us an equivalent result, or these two are in fact equal. And we're going to do that by comparing two numeric examples. So we're going to have log, and instead of a strange base, we're going to just use base 10 of 15 to the power of 2. And we're going to prove to you that that's the same as 2 times log base 10 still of 15. So again, grab your calculators and see if you can get the same answer in both cases. What you see is exactly what we anticipated. If you type in the log of 15 squared, so you keep that argument squared and you house those things in the brackets, you'll get the same value. So it's about 2.35. You'll get the same value if you type in 2 times the log of 15. So again, power rule means you can put something in a power position, or you can bring that power out front if it was part of the argument and make it a coefficient instead. So to work with this power law a little bit, we want you to write each of the following in the form n times the log of x. So the first expression we're given is log base 2 of x to the power of 5. I'm not asking you to evaluate anything. I just want you to rewrite it as n times the log of x. So essentially what has to happen is we need to take this power and move it in front as a coefficient. So what we end up with as an equivalent expression is 5 times log base 2 of x. So we're preserving the base. We're just moving that power from a power position into the coefficient position. The same thing can happen with part B, but this looks like a little bit of a hot mess to start. So we've got log base 5, and it's supposed to look like the cubed root of x squared. Sometimes those symbols don't show up very well when we're using things like PowerPoint. So please rewrite this as log base 5 of the cubed root of x squared. Now, in order to use the power law, we need to create a power out of this radical. What we know is that we can rewrite this as log base 5 of x to some power. If you have the cubed root of x squared, that power, of course, is going to be 2 over 3, where again, the numerator is the power that's associated or assigned to the x. The denominator of the fraction is always the index or the type of root that we see. Now what we can do is take that power and move it in front as a coefficient. So an equivalent expression would be 2/3 times log base 5 of x. In our next example, we're going to use exactly the same laws, but instead of writing it with your power out front as a coefficient, we want to write these expressions in the form log of some base, or in this case base 10, of x to the power of n. So if we look at our first example, we've got 1/2 log x, and again, this is a base 10 log. What we know is that instead of being out front as a coefficient, that 1/2 can be moved into a power position. So instead, we can rewrite this as log still base 10 of x to the power of 1/2. Again, these skills of sort of converting things back and forth or using these laws is going to become very handy when we get more complicated processes a little bit later in our module. Part B, very similar. We've got -2 log base 10 of x. So once again, if we have a coefficient in front of that log, we can tuck that coefficient back up into a power position and say we get the same answer if we evaluated or used log base 10 of x to the power of -2. If you really want to get creative, that's the same as saying log base 10 of 1 over x squared. Remember, we can pack up and move that negative exponent, but be careful, it's still a base 10. And we're still talking about 1 over x squared as the argument. I'm perfectly happy if you leave your answer at that stage. The next example looks a little bit more complicated at first glance. So question number 7 says, use the law of logarithms to rewrite the following expression as a single logarithm. So right now I see there are 1, 2, 3, 4 separate logs in that expression. We want to combine them and make them one. So as I'm rewriting this, we've got 3 log base c of x plus 2 log base c of w. We're then subtracting inside brackets log base c of 2 plus log base c of 5. So we can kind of think about this like BEDMAS rules. If you really wanted to, we could attack the things inside the brackets first. But aside from that, what I'm noticing is that these coefficients might be in the way. If we combine 2 logs, so let's say we wanted to combine the first 2 terms, I know that because they're being added, we can use the product law. Now the problem is, what do we do with that coefficient of 3 and what do we do with that coefficient of 2? So instead of getting lost in the shuffle or maybe performing the wrong operation, what I'm going to do first is take those coefficients and put them back with their associated bases. So I'm going to use that power rule sort of in reverse. So the first step for me would be to take log base c of x and rewrite it now to the power of 3 and add that to log base c of w now to the power of 2. If you want to rewrite the rest of the terms, you're welcome to, but I'm actually going to absorb the next little piece in one step. So if I look inside those brackets, those are both log base c. And again, what I'd like to sort of really make sure you're aware of is that these quotient rules or product rules or power rules are all being utilized when the bases in your expression are all the same. Because these are all base c logarithms, it's okay for me to combine them or make them one. So inside those brackets, instead of having log base c of 2 plus log base c of 5, that plus sign tells me I can use product rule. So this really becomes log base c of 2 times 5. And again, we'll clean that up in just a second. Now, in the first two terms, we're still sort of adding two separate logs, and those two separate logs are still base c. So we can combine them or put them together as one using our product rule. If we do that, we'll now have log base c of x to the power of 3 times w squared. So product rule puts those together. If you don't want to do anything else in that step, you can say now I'm subtracting log base c of 2 times 5. And if you want to rewrite that as 10, you're welcome to. Now the last step is to combine these last two logs because once again, they're both base c. We can combine them using our quotient rule. So quotient rule says when you're subtracting two separate logs that have the same base, you can put them together using division. So to rewrite this as one term, you would have log base c out front, and your argument would be the rest of those pieces combined. So you'd have x to the power of 3, w squared, all divided by just 10. Please be mindful that when you're using the product rule or the quotient rule and you're combining logarithms, I only want to see one log out front. If you put a log in the numerator and in the denominator, it's a very different value and it's not equivalent. So just be very careful when you're combining that you're only writing, in this case, log base c once, and that's in front of your quotient. Now, the last few examples are asking you to evaluate, and I'm going to challenge you to do this without your calculator. You're not going to need a calculator for this, and actually there are multiple ways you can tackle the same problem. So if we take a look at 8a, what we have here is log base 3 of 9 to the power 2. Now, there are a couple of ways I can deal with this. If I don't want that power of 2, I can move it out front and make it a coefficient. So we can call this 2 log base 3 of 9. We can also use some of the shortcuts we know from before and say that if the base of the log matches the base behind it, we can kind of simplify in a really slick or quick way. So we can rewrite this as 2 times log base 3 of 3 to the power of 2. Now, because the base of the log matches the base behind it, essentially those things disappear, and we end up with 2 times 2. 2 times 2 just gives us 4 as a final answer. Now, some of you might be asking, can't we just make this 9 a base 3 from the beginning? And the answer is absolutely. That's still legal. That's still a good step. So as an alternative, if that's the approach you wanted to take, we could say this was really log base 3, and instead of 9, call that 3 squared. It's still raised to the power of a 2. So we know power of a power means multiply. So if you have log base 3 of 3 to the power of 2 times 2 or 4, we still have the base of the log matching the base of the argument behind it. So our little trick to simplify is to say, well, our answer, or our final answer in this case, is still just 4. With part B, you can take a very similar approach. You can use, as long as you're using these laws correctly, it doesn't matter what combination you put them in. So here we've got 5 log base 6 of 36 to the power of 3. If that power of 3 is bugging you, go ahead and move it out front. What happens is there's already a coefficient there, so those two get combined using multiplication. So what we end up with is really 5 times 3 out front, or 15, times log base 6 of 36. We know that 36 is a base 6 number, so we can rewrite this as 15 rather, log base 6 of 6 squared. And because the base of the log matches the base behind it, we can sort of ignore those things. And this becomes 15 times 2, or 30, as our final answer. Now, if you didn't want to do that, let's say you wanted to take that coefficient and move it out front. So I'm going to redo the same question. If we take 5 log base 6 of 36 to the power of 3, what we could do is take this coefficient of 5 and combine it with the existing power on that 36. So this would become log base 6 of 36 to the power of 5 times 3, or 15 here. Now we're almost ready to use that simplifying trick. We just have to make 36 a base 6 number. So we've got log base 6 of 6 squared. Again, that's still raised to the power of 15. So we know power of a power means we multiply those things. So we've got log base 6 of 6 to the power of 30. And once again, the base of the log matches the base behind it. So we can ignore those things and know that our final result, or our final answer in this case, is 30. There isn't a whole lot of simplifying with the next one. In part C, we've got log of 10 to the power of n. What I want to remind you of is that we don't see a base, but if we don't see a base, we know it's a base 10. So in this situation, we have log base 10 of 10 to the power of n. So we know we can simplify, and our final answer is just n. If you didn't want to do it that way, again, the alternative is to say, let's take that power of n and rewrite it as a coefficient. So you could have n times the log of 10. Now, once again, we know that there's an imaginary little base 10, but we also know that the power that's stuck to that 10 in the argument is power of 1. So when the base of the log matches the base of the argument, we ignore those things, and we end up with n times 1, or just n, as we had for a result the first way we tackled the same problem. The last example might be the most challenging. In this case, we're going to approach this by saying if you have 6 log base 25 of root 5, that radical is kind of posing a bit of a problem, and maybe the bases don't match as nicely as we would want them to. So the first thing I'm going to do is rewrite that root 5 as some rational power instead. So here we have 6 times log base 25 of 5 to the power of 1/2. So I've gotten rid of that root sign by making this a rational exponent. What I also want to do is sort of clean up this term, and instead of having 6 out front as a coefficient, I'm going to move that into the power position. Now, I know there's already a power there, so we've got log base 25 of 5 now to the power of 6 times 1/2. So over in the margin, if we had 6 over 1 and we were multiplying by the half that's existing, we get 6 over 2, or just 3. So I'm going to clean up that power and say this is really log base 25 of 5 to the power of 3. Again, we're just multiplying that coefficient in the power position with the existing power that was there of 1/2. Now, this would be really great if 5 to the power of 3 was a nice, easy base 25 number, but these are kind of linked. What I'd like to point out is that if you're ever stuck, if you're ever trying to find an answer, sometimes it's easiest for you to make an equation out of it. So I'm going to take this expression, log base 25 of 5 to the power of 3, and I feel like I'm sort of stuck here. So I'm going to say, let's make this equal something, right? So we've done this in class before. We've taken expressions and we said, if we give this a value, so you can call this Q or R or X or Y, what we're doing is we're setting up a little bit of an equation. Now that we have set up a little bit of an equation, this logarithmic form isn't serving us very well. So what I want to do instead is convert it. And by convert, what I want to do is convert to exponential form. This is something that we've been practicing at length. So if I convert this to exponential form, I like to start with my base. So 25 is my base. My power is power of x, and that's going to be equivalent to the argument, which is really 5 to the power of 3 right now. So I have a base 5 on the right side. On the left, it's almost base 5. We can just rewrite that as 5 squared. 5 times 5 is 25. Still raised to the power of x. That's equivalent to 5 to the power of 3. So if I clean up those powers, we have 5 to the power of 2x equals 5 to the power of 3. And now that our bases match, we can kind of ignore them and say, in this case, 2x must be 3. So from here, if we divide both sides of our equation by 2, we get an x value of 3/2. So if I were to evaluate 6 times log base 25 of root 5, my final answer would be 3/2. So this one took a little bit of creativity. So we wanted to make sure that our bases matched, but they weren't quite as nice as we had hoped. So we then employed the strategies that we've been using in class to say, if we're stuck, we can convert to exponential form, and that'll help us make sure that those bases can match and that we can solve the resulting equation. So that's it, folks. This lesson was all about the product law, the quotient law, and the power law, and basically using them in combination to do things like simplify, evaluate, or rewrite some of those expressions. What you're welcome to do now is tackle the regular homework questions that you see at the bottom of the slide. And as always, if you have any questions, please don't hesitate to reach out. I'll be happy to help.